In this video, we are going to look at volumes of solids of revolution. Uh, we will be focusing on volume of revolution using disks and washers method. Disk and washer method to find the volume of a solid. This method is used to find the volume of a solid obtained by rotating a solid either along the x-axis or along the y-axis or along one of the lines like x equals 1, y equals -2, or any other horizontal or vertical line. We will start looking at the volume of solids of revolution. We should first define just what a solid of revolution is. To get a solid of revolution, we start out with the function y equal to f of x on an interval a to b. Then we rotate the curve about a given axis. So here, for example, if this was my curve, the one you see on the right, and I rotated about x-axis, I would get something like this. And that would be my solid of revolution if I rotated about x-axis. On the other hand, if I rotated about y-axis, it would look something like this, and I would have a solid of revolution like this. Okay, so that's just an example of what a solid of revolution is. Okay, axis, it could be any vertical or horizontal line. Doing this for the curve above gives the following three-dimensional region. So if you rotate it about x-axis, here's a better picture than the one I showed. Again, this is not the shape made up of plane surfaces. It's got curved surfaces. In geometry, we have no way to find the volume or surface area. But using calculus, we can find the volume and surface area of a shape like this. Okay, so this would be called a surface of revolution. This is a surface of revolution because we rotated the curve f of x over the x-axis. Okay, so we want to determine the volume of this solid. Cross this out. Whenever we need to find the volume of this solid, we basically will be dividing that solid into disks or washers. Disk is something like a compact disc CD that does not have any holes in it. It's a full circle. Washers have holes in them. Okay, the volume will be the bounds A to B, area of one disk times the width of one disk, which is dx. If your disks, for example, if you look at this picture, your disks are perpendicular to x-axis, the width of disk will be in terms of delta x. Okay, you can see the comparison between disks and washers. This picture have disks. There's no holes in the middle. It's all closed circle. Looks like oval, but if you imagine in a 3D shape, these will be actual circles. And the other side picture, because you're gonna have a hole in the middle, you are dealing with washers. Okay, so when you're dealing with the disks, we need to find the area of each disk, which is pi r squared, and multiply with the width of the disk, which is delta x. And that would be the volume of one disk, and we will integrate the volumes of small disks from point where the disks start to the point where the disks end. Okay, so we have disks and washers method. In terms of disks, we will be using this area equals pi r squared to find the area. In terms of washers, we will be using pi. R is the outer radius and lowercase r is the inner radius. Okay. All right, so let's take a look at a couple of examples. Here's the first example, rotation about x-axis. All right, so every time you could be rotating about x-axis, you could be rotating about y-axis, you could be rotating about other one of the vertical or horizontal lines. So I'm gonna go ahead and graph square root of 4 minus x. So how does that graph look? Okay. Square root of 4 minus x. Let me quickly check on Desmos. I'll show you the graph on y equals square root is here, 4 minus x. This is how the graph looks. And we only need to worry about first quadrant. So we're only going to be looking at this little piece, okay, the first quadrant piece. All right, so let's go back to the notes now. Here's how the first quadrant looked like. All right, so we want to find the volume of solid obtained by rotating this curve about x-axis. Okay, so my goal is to rotate it about the x-axis. And I'm going to have a shape that looks like this if I rotate it about x-axis. This is x-axis and this is y-axis. As you can see, I am going to have discs in this case, not washers because there's going to be no holes. And width of each disc would be in terms of delta x, because as you can imagine, the slice, thickness of the slice is on the x-axis. Okay, so area of each disc, let's go ahead and think about area of the disc, area of one disc. Area is going to be pi r squared. It's a circular disc, so full circle, pi r squared is the area. Okay, I need to think about the radius. What is the radius of the disc? So let's go ahead and think about, this is the radius of the disc, and I can see it's the y value. Radius is the y value, but we want in terms of x, because our integral will be in terms of x. The width is delta x, and we want the entire integral in terms of x. Okay, so the area is pi r squared. The radius is the y value, which is this. We want it in terms of x, so it's 4 minus x squared. So it would be pi times 4 minus x. This is the area of one disc. What's going to be volume of one disc, or volume of the disc we are talking about? Volume is going to be area times the width, which is delta x. Now we want to find out the volume of the solid. Okay, so volume of the solid is going to be integrate all the volumes of these discs, small discs. So we can have a very small disc all the way here, and discs all the way up to the y-axis. Okay, so I need to figure out, the discs start at x equals 0. I see that, but where do they end? So I need to see, where does this curve touch the x-axis? This curve touches the x-axis when y is 0. So I can say 0 equals square root of 4 minus x, which gives 0 equals 4 minus x, or x equals 4. So this curve touches the x-axis at 4. That means my discs are going to end at 4. So I'm going to have all these parallel discs that I'm trying to integrate the volume from 0 to 4. Okay, and pi r squared, delta x becomes the operator dx when we integrate, and that is a definite integral. Once we integrate, it would be 4x minus x squared divided by 2 from the bound 0 to 4, and that comes out to be 16 minus 16 divided by 2. We don't need to worry about subtracting the 0. It's all going to be 0. So the volume of the solid comes out to be 8 pi. Okay, so volume of the solid created comes out to be 8 pi. The first thing you want to do is draw the picture, figure out where are you touching the x-axis, where you're touching the y-axis. Those are going to be your bounds. Here's the next example, rotation about y-axis, the same curve from last example. We're going to rotate it about y-axis now. Okay, so my curve did look something like that. And now I want to rotate it about the y-axis. So if I rotate it about the y-axis, I am going to have something like this. Maybe I'll go a little farther. So where does it touch the y-axis? As you can see, it is going to touch the y-axis. It's touching the x-axis at 4 here. It would touch the x-axis at -4, but on the y-axis, where does it touch the y-axis? When the x is 0. So we can find out by plugging x as 0, which turns out to be square root of 4, and that's a 2. So it touches the y-axis at 2. Now imagine your discs. In this case, you are going to have discs parallel to x-axis. Again, there's no holes in there, so that's nice. The width of each disc is in terms of delta y now. That means we want our whole integral in terms of y. Our bounds of integration will be also the y values. Okay, so let's go ahead and find out area of the disk. Area of one disk we are considering. So area of the disk is pi r squared. What's the radius in this case? The radius is actually going to be the x value at this point. If you look carefully, the purple one oh my god, I did not want the eraser. Anyways, I'll just complete my disk again. And the radius, you can clearly see radius is the x value at that point. But we want it in terms of y. So radius is the x value, but we want it in terms of y. In terms of y. We want it in terms of y, okay? In terms of y. So what I'm going to do is I'm going to solve that given curve for x value in terms of y. I'm going to square both sides. And then I can say x is equal to 4 minus y squared. That is my radius here, x equal to 4 minus y squared. That is the radius. So area of one disk comes out to be 4 minus y squared is the radius, pi r squared. That is the radius of my curve. Okay, what is the volume of one disk? So volume of the disk is going to be pi r squared times delta y. So it's pi 4 minus y squared times delta y. Again, I'm ready to write volume of the solid now. When we get the volume of solid, we integrate all the volumes of disks from wherever they start to wherever they end. The disks start at 0 and they end at 2, and pi 4 minus y squared dy. Okay, let's go ahead and simplify this integral. Evaluate the integral. I would have to open up the square. So that's going to be 16 minus 8y squared plus y to the 4th dy. And that all turns out to be, when we evaluate, 17 pi. Okay, I just use a calculator, but you can give it a try. Make sure you know how to do it. Just really just plugging in the bounds. All right, so we rotated the same curve about x-axis and rotated the same curve about y-axis. You notice the volumes are not the same. So you're not going to get the same volume because you rotated about the x-axis or y-axis. Okay. All right, the next example we are going to look at, find the volume of solid when y is equal to 4 minus 2x is revolved around x-axis, and then we want to revolve it around the y-axis. So this problem has two different parts to it. Make up some space for it. So first of all, I'm going to draw the shape here. Y is equal to 4 minus 2x. I like to think of it as negative 2x plus 4. So I have a line with a negative slope. Okay, I should say somewhere in quadrant 1. So only quadrant 1 piece is the one that we're considering. Okay, so I'm gonna add that quadrant 1 in the discs and washers problem. I'm just making a note to myself for correction. Quadrant 1, page 21. Okay. All right, so that is going to be a line that looks like this. Where does it touch the y-axis when x is 0 at 4? Where does it touch the x-axis when y is 0? And that's going to be at 2. Okay, so first of all, we want to rotate it about the x-axis. Let's do that. So this is rotation about the x-axis. When I rotate this curve about x-axis, so I'm going to have a solid that looks like this. Actually, we can use, this would be a triangle. Now, if we rotate it, it would be like a cone. Okay, so we are going to have discs here. Again, no holes in the middle, which is nice. We're going to have discs here. So I'm going to go straight, setting up the formula for integration for volume of the solid. Okay, we know what goes in the volume of the solid. We need to integrate area of one cross section times the width and then the bounds from A to B. Now in this case, your discs have the width in terms of delta x. So I'm gonna have dx with the integral. What's the area of one cross section? Well, area is pi times the radius squared. The radius is the y value. If you look carefully, radius is just the y value at each point. And we want that y value in terms of x, which is given in that relationship, 4 minus 2x squared. And where do the discs start? They start at 0 and they go all the way up to 2. Okay, so my bounds of integration will be from 0 to 2. Now, go ahead and evaluate this integral. It is going to come out to be 32 divided by 3 pi. Okay, that's just evaluating the definite integral. Okay, now let's do the same problem. We want to revolve this this line about the same, touching the x-axis at 2, y-axis at 4. Now we want to revolve it about the y-axis, and we can have discs. They're going to be perpendicular to y-axis. So width of each disc in this case would be delta y. Okay, again, I'm going to set up the volume of the solid would be bounds of integration. Wherever the discs start, they start at y equals 0 and they go all the way up to y equals 4. So from 0 to 4. Pi r squared. The radius, what is the radius in this case? The radius is each x value. So the radius is the x value, and we want it in terms of radius is the x value. We want it in terms of y because my discs are perpendicular to the y-axis. Okay, which would be, I'm just gonna isolate y, I'm just gonna isolate the, so we're given y is equal to 4 minus 2x. I can say 2x is equal to 4 minus y. X equals 4 minus y divided by 2. Okay, so my radius is 4 minus y divided by 2 squared. That's the x value. And the width will become the operator dy whenever we are integrating. And evaluating this integral, this turns out to be 16 pi over 3. As again, you can see, if you revolve the same curve about x or y axis, your volumes are not going to be the same. Okay. So the next example, we are going to find the volume of region enclosed by y equals x plus 1 and y equals 2 from x equals 1 to x equals 4 about x-axis. Okay, a lot going on in this problem. So let me go ahead and draw the shape first. y equals x plus 1, that is a line that looks like this, starting at 1, go up 1 over 1, right? Yep, line with the slope 1. This is the line. And y equal to 2. Y is equal to 2 is here. Okay, from x equals 1 to x equals 4. Okay, so we actually only want this much of our shape because of all the restraints given to me. We don't want the rest of the line, so I'm gonna go ahead and erase the rest of the line. We don't need this. Okay, we only want to rotate the shape that we did draw. All right, we want to rotate it about the x-axis, so this is my axis of rotation, and I think I'm gonna have something like this. Too big of a triangle, probably not gonna be that big. Something like this. Okay, after the rotation, my solid will look I would have discs and wash. Actually, in this case, it would be the washers, no discs. So I'm just drawing one disc for your reference. We're going to have discs all the way from 1 to 4 in this case. Discs all the way from 1 to 4. Okay. All right, so let's go ahead and go through this. Okay, so let's first think about area of 1. We have washers in this case because there's gap in the middle. There's holes in the middle for these washers. We don't have anything over here that's a hole. Okay, so region that I kind of shaded in the middle is a hole that's empty. So there would be holes. Area of 1 washer. That would be pi outer radius square minus the inner radius square. Okay, let's go ahead and think about what is the outer radius. First of all, thickness of each washer will be in terms of thickness of each washer will be in terms of delta x. Will be in terms of delta x. Thickness of each washer will be in terms of delta x because discs and washers in this case, washers are perpendicular to the x-axis. Okay, the outer radius, we want everything in terms of x. Okay, the outer radius is the y value. If you look at it, outer radius is this purple y value. How do you find that y value? That is actually defined by the curve x plus 1. So my outer radius is x plus 1 squared, and the inner radius, let's make it a little different color so it's easy to see. Inner radius is this much yellow. It's a little hard to see the yellow color, but this is the inner radius. The outer radius is changing as you go towards right. The x plus 1 is changing, it's increasing, but the inner radius is constant, it is 2. So the inner radius is not changing. Okay, so it's just 2 square. All right, good. We have area of 1 washer. What's the volume of 1 washer? Volume of a washer. Volume of the washer, volume of 1 washer, whatever you want to call it, doesn't really. Volume of 1 washer, volume of 1 cross section. That is going to be the area times the width, right? Area times the width. Width in this case, we already decided that it's delta x. All right, now I'm ready to write volume of the solid, because if you know volume of 1 washer, all you have to do is integrate those volumes over the range where you have your washers. Volume of the solid is going to be, what are going to be the bounds of integration? Well, you can see your washers are going to start at 1 and they're going to end at 4. So from 1 to 4, and then pi x plus 1 squared minus 4 dx. Okay, go ahead and evaluate that integral. I believe it's going to come out to be 27 pi. Check with your calculator, or check manually, work it out and check and make sure this is the right answer. Okay, that's an example with the washers in there. Some you can have some problems with both discs and washers involved in there. Okay, next problem. Here we are. I'm actually gonna have you guys go ahead and try this and check with me when you're done. Okay, so go ahead, I'm gonna pause. You try, pause for a minute, try the problem, and we will check back. Okay, y is equal to square root of 9 minus x squared. It is going to look something like this. Double check with Desmos. Square root of 9 minus x squared. All right, yep. That's just a circle, top half of the circle. So all right, so that's the top half of my circle. And we are going to rotate it about, let me make it a little nicer shape. We want to rotate it about x-axis between x equals -2 and x equals 3. Okay, so not just the first quadrant, but we're going to consider the shape between x equals -2 and x equals -3. So it is touching the x-axis at +2 and -3, but we are being told not to go all the way to -3, so just between -2 and 3. If I rotate it over the x-axis, let's see what happens. I'm going to have a shape like this. Okay, it looks a little bit bigger than what it should. Okay, that's better. All right, so I want to find volume of this solid, and we have rotated about the x-axis. If we rotate it about the x-axis, then I already know my discs will be, there's no washers here, so discs are perpendicular to x-axis. That means the width of each disc will be in terms of width of each disc is delta x. Okay, what else? So width of each disc is delta x. All right, discs are perpendicular to x-axis. Width of each disc is delta x. Okay, so we want to find out area of one disc. Area of one disc. To find the area of one disc, well, I need pi r squared. That's the area of a circle. But I need to think about the radius because we don't know what the radius is. Let's see. The radius would be each y value, but we want it in terms of x. Okay, so this is the radius. It is the y value. We want it in terms of x, and that's already given to me. So I don't need to do any work to find that out. So pi times r squared, which turns out to be pi times 9 minus x squared. Okay, pi r squared is the area of one disk, pi r squared. All right, so what's the volume of one disk? Volume of one disk would be the area times the width of one disk, which is delta x. This is the volume of one disk, and we are ready to find volume of the solid now. So volume of the solid is going to be, I'm going to have to integrate wherever the discs start and wherever the discs end, and it looks like discs will be starting at -2 and they will be ending at +3. And the area of each disc, and delta x becomes the operator dx. Okay, so 9 minus x squared between negative 2 to 3. And go ahead and evaluate that integral and check with me. It comes out to be 100 pi over 3. That is the volume of the solid obtained by rotating this solid over x-axis. All right, next example. Find the volume of solid generated by y equals x plus 1 and y equals 2 from x equals 1 to x equals 4 about the line y equals negative 1. Wow, a lot given here. Okay, it's similar to the curve that was given earlier. So y is equal to x plus 1 and y equal to 2. That looks something like this. X plus 1 and this is y equal to 2. From x equals 1 to 4. Okay, we did a problem similar to this. I think at that time we rotated about the x-axis. Now we are rotating about the line y equals negative 1. So my axis of rotation is not one of the axes now. So this is how after rotation my shape is going to look like. So I'm going to have discs, actually not the discs, the washers in this case, because there's a hole in the middle. Okay, there's washers because there's holes in the middle now. All right, so let's go ahead and think about area of one disc. Area of one disc. I'm sorry, not a disc, area of one washer here. Area of one washer. What's the area of one washer here? Well, because we are dealing with washers, we have an outer radius and an inner radius. The outer radius is defined by x plus 1. There's no change to the outer radius, but there is slight change to the inner radius, so it's pi. The outer radius is defined by x plus 1 plus 1. Okay, it's going to be x plus 1 squared. Why am I adding the 1? Because the y value from here to here, the y value is x plus 1, but your radius is actually all the way up to here. So adding that extra 1, because your axis of rotation is y equal to negative 1. So this is going to be your outer radius minus the inner radius. From here to here it is 2, but then we also have 1. So altogether the inner radius will be 3. Okay, so that is what I have here. So this turns out to be pi x plus 2 squared minus 3 squared. That's the area of one washer. Once you have the area of one washer, we are ready to write the volume of the solid. The volume of the solid is going to equal wherever the discs or washers start. They start at x equals 1 and they end at x equals 4. So from 1 to 4, the area of one washer, it's x plus 2 squared, pi r squared, pi outer radius squared minus inner radius squared, and the delta x width will become operator dx. Okay, go ahead and evaluate that integral and check with me. I got 36 pi. Okay, that's the volume of this solid. All right, couple more examples. Actually, no more examples. This should be enough for the discs and washers. We will also look at shell method in the next video for finding the volume of a solid.